Alright, now energy stored in a capacitor. Okay, so we need to find a formula how to calculate the energy stored in a capacitor. Okay, so if you want to charge a capacitor, first of all, you need a battery. Okay, you need to connect the capacitor to a battery. So the battery will do some work. Okay, will do some work to charge a capacitor from zero charge up to the maximum charge. Okay, so after the battery has done the work to charge a capacitor, so all the work done by the battery will be stored in the capacitor as electric potential energy. Electric potential energy. Still remember what you learned about electric potential energy in the chapter 1, electrostatics, where you learn about this formula. Electric potential energy is KQQ over R. Yes, this is the kind of energy stored in the capacitor. Yeah, the electric potential energy. Yeah, not kinetic energy, not elastic potential energy, but it is the electric potential energy. Okay, of course, but we don't use this formula KQQ over R to calculate the electric potential energy in the capacitor because there are many charge stored inside the capacitor, not just one or two electron. For this KQQ over R, is like a microscopic calculation for electric potential energy. Maybe it just involve one or two charges, one or two electrons, one or two charges. But if you want to calculate the electric potential energy stored in the capacitor, we have another formula. Okay, and that is the formula we need to find out. Okay, so whatever work done by the battery will be stored inside the capacitor as electric potential energy. Okay, and this electric potential energy is the same as the electric potential energy we learned in first chapter, electrostatic. Yeah, KQQ over R. Okay, so now let's find out the formula. Work done by battery to charge a capacitor from zero charge to maximum charge actually is integration between voltage versus charge. Integration, we normally say when involved about integration, means it need to find area under this graph, under the voltage charge graph. So when you learn in the mathematics, integration is to find the area under the graph. Okay, so this is the area under the voltage charge graph, and this is the voltage charge graph that has been drawn. I will explain about this graph later. First of all, we look at how to do the integration mathematically. Okay, integration voltage charge. We know that the voltage is changing because initially the capacitor is neutral, voltage also neutral. Okay, voltage also neutral across a capacitor. But this is the initial because the capacitor is not charged up, so the voltage is zero, charge also zero. Yeah, for capacitor, VC 0, QC 0. But after charge to the maximum finally, the voltage of capacitor will be equal to the EMF because the capacitor is parallel to the battery. Yeah, parallel to the battery. So finally, the voltage of capacitor will become the same as the EMF of the battery, and the charge of the capacitor also reach the maximum charge. Okay, so basically is the voltage from zero. If you look at the graph, the voltage is zero. Yeah, zero charge to voltage equal to EMF. So voltage increase from zero to EMF. Same goes to the charge. From zero charge go to maximum charge. So that's why the graph is increasing. Do you see that? The graph is increasing because the voltage from zero voltage, neutral, become maximum voltage, EMF. Yeah, why equal to EMF? Because it is parallel to the battery. They must achieve the same voltage. Yes, they must achieve the same voltage. and then the charge also from 0 charge, the battery has charged a capacitor from 0 to maximum charge, from 0 charge to maximum Q. Okay, so the Q also increasing, the V increasing, the Q increasing. Okay, so let's look back to the formula. We know that both this voltage increasing, charge increasing, that means the voltage and the charge both changing, isn't it? Both changing. So if you want to integrate the voltage, we must find a certain constant value. So both of these variable change. Both of these variable change. So this voltage we have to change to this formula. We know that Q equal to CV, isn't it? Q equal to CV. And then we change the formula a little bit. It become a voltage equal to Q over C. So remember the formula we learned in earlier videos. Q equal to CV. So we just change to this formula. Okay. We want to put the voltage in front. So C go below. So that's why V equal to Q over C. So we change it to, we need this. We need this Q because we are integrate against Q. We integrate against Q. So we change the V to Q over C. If not, we don't know how to integrate, isn't it? So we change the V into Q over C. Now it's possible to integrate. Q over C. Use your integration knowledge you have learned. Okay. Yeah, this is the integration of V VQ is actually area under VQ graph. So change the V into Q over C. Okay, we know that the C is a constant value. Okay, C is the same capacitor, isn't it? C never change. C is a constant value. So C can be taken out. No need to integrate because a constant can be taken out from the integration. Okay, taken out and then left with only Q. Now you can integrate Q dQ. Integrate Q. So Q become Q squared over 2. Q squared over 2. And then you integrate from 0 to charge. That means you charge the capacitor from 0 charge up to maximum charge. Okay, 0 to maximum charge. So you got this. Q squared over 2 minus 0. Yeah, minus 0. So minus 0, you just ignore. So left with half Q squared over C. So this is the work done of battery to charge a capacitor from 0 to maximum charge. So you got the formula for the electric potential energy stored in the capacitor. So just that easy integration, and you got the formula, half Q squared over C. And then we know that Q equal to CV. We apply back this formula. We substitute, and then Q we substitute with Q. We substitute the equal to CV, so you get C square V square over C. So that's why you get half CV square, half CV square. And we can also further substitute this formula into this CV here. So you get half QV. Okay, half QV. And this is the energy stored in the capacitor, which is the we call it elastic potential energy. No, it's called the electric potential energy stored in capacitor. Okay. So that's why we don't always say that capacitor only store charge. Sorry. Again, we don't always say capacitor always only store charge. Yes, of course it store charge. Capacitor of course store charge. But do you know that when it store charge, at the negative plate, it build up the electric potential energy. It build up the electric potential energy stored in the capacitor. Do you know that? Because you are bringing all the electrons from the other plate, from the positive plate, together, to become close to each other at the negative plate. You are bringing all the electrons which have the same charge, which repel each other, to bring it at a close proximity at the negative plate. So of course, it built up a very high electric potential energy at the negative plate, which is the KQQ over R. That's why we say that capacitor stored electric potential energy. Do you understand that? Okay, it stored electric potential energy. Don't just always say that capacitor store charge, store charge. Yeah? Your knowledge just limited to that. The capacitor only store charge. The capacitor actually stored electric potential energy, which later on, this energy will change to kinetic energy when discharging process. That means this electric potential energy will help the electron to flow in the external circuit to light up the LED, to light up whatever electrical components. If you start to use the capacitor, you start to discharge a capacitor, the electrons start to flow in the circuit. This electric potential energy will change to kinetic energy to make the electron flow in the circuit. Then the electron will start to flow. Why it flow? Because the electric potential energy now change to kinetic energy to help the electron flow in the circuit. You understand that? So that's why a capacitor stores certain kind of energy. We call it electric potential energy. And the formula is half Q squared over C, or half CV squared, or half QV. Both of these three formula can be used depending on the problem solving. Yeah. So if the question gives you Q and C, you just use half Q squared over C. If the question gives you C and V, you just use half CV squared. If the question gives you Q and V, you just use half QV. But depend on the formula, you must be wise enough. I will talk about how to use this formula later on in the problem solving. Okay, now I want to explain a little bit more clearer about this graph because it involves a little bit of concepts. Before we go into this graph, you know already the graph is increasing, increasing like this because the voltage increased from 0 to maximum voltage equal to EMF. The charge also from 0 to maximum charge. We know that the graph increasing like that, So that's why you see, since the graph increase like that, that's why the area, just now you learned about the integration, the area under the voltage charge graph, is the potential energy. Do you know that? Just now the area you learned just now, this is the electric potential energy. That's why it's half QV, half QV. The area, the integration, the integration, never mind. The integration means the area under this VQ graph is the electric potential energy. So it is a triangle, isn't it? So half times base times height is half times base times height is the area of the triangle, half QV, which is also the electric potential energy. See that? There are many ways to explain, not just by integration, you can get the electric potential energy. By drawing the graph itself, also you can easily find out the formula half QV, area under the graph, which shows the electric potential energy stored in the capacitor. Okay, a more clearer why is it the graph increasing like that? One way is to say that the V increase, the Q increase like that. But there's another way to explain this, by looking at the circuit. Okay, before we go deeper into this, I want to recall. I want you to recall back what you have learned in the first chapter. In the first chapter, about the electric potential energy KQQ over R. Okay, so we make it specific, the condition specific to the capacitor, where when you charge a capacitor, you are bringing all the electrons from the positive plate to gather at the negative plate. So you are bringing all the electrons become close to each other to just gather at the negative plate. See, look at step by step. You have the first charge, you have the second charge, you have the third charge, you have the fourth charge. We look at charge by charge. Okay, all of these charges are electrons because only electrons flow in the circuit. Only electrons flow in the circuit. So all of these are electrons. Okay, so the formula is KQQ over R. So since we are talking about only electrons, That's why the Q is actually negative E. The Q is negative E. Okay, Q is negative E. So if you want to calculate the electric potential energy, is KQQOR. The Q is substitute with negative E. Still remember the negative sign is very important. The negative sign you must show, yeah, because negative sign in the potential energy means the magnitude. So when you want to find the potential energy, the scalar quantity, the charge must have negative sign. The charge must have negative sign. So we substitute the negative sign together. So charge Q is negative E, Q2 also negative E. So when you have two negative become positive. So the negative just gone. So it become electron. This is electron charge. So you get Ke squared over R. Yeah, for each of them. Okay, distance is almost the same. Yeah, because they are close to each other. They almost have the same distance. That's why I just use R. Okay, now look at one by one. Yeah, one by one. To find the electric potential energy of the system, we talk about system because we have talked about many charges. Many charges gather at the negative plate. System of all charges. So we always look at, since we have a few charges, we look at how they interact with each other, isn't it? But we look at one by one. Yeah. First of all, I want to talk about the first charge. The first charge. You are bringing the first electron. You are bringing the first electron from very, very far away, infinity. Actually, this charge comes from the positive plate. But I assume as from infinity. Initially, the negative plate is not negative yet. It's not negative yet. It's still neutral. Yeah. Initially before charge. Actually, before charge, initially the capacitor is neutral, isn't it? Capacitor is neutral. The negative plate actually is not negative yet. It's this neutral. It's still neutral. There's no charge here. There's no charge here. Okay, there's no charge here. So when you bring in the first electron to the negative plate, actually very easy. Very easy. You're very easy to bring the first electron to the negative plate because there's no charge. There's no other electron. There's no other electron yet at the negative plate. So you can easily bring this electron to that plate. So actually there's no work done. There's no work done. Zero work done. You see that? You see, work done one is actually zero work done. Because there's no repulsion force. There's no other electron at this plate. So when no repulsive force, you easily bring this electron from the positive plate to the negative plate without any work done. Zero work done. Okay? Okay. Now, you already bring the first electron to that plate. Okay? Now, in the negative plate already have one electron. And one negative charge. Now, you are bringing the second electron from the positive plate to the negative plate. This second electron is a little bit harder to bring it to the negative plate. A little bit harder. Because why? Because now the negative plate already have one electron. So you want to bring the second electron to the negative plate. The second electron will experience the repulsive force from the first electron just now. Repulsive force. So there are some work done need to be done to overcome the repulsive force. So what is the work done? That is U12. The interaction between charge 1, which is now already in the negative plate. Interaction between 1 and 2. Between 1 and 2. So what is the work done needed? U12. That's what you learned in first chapter. U12, which is K Q1 Q2 over R. The interaction between Q1 and Q2. So just now we already found the formula K Q Q over R, and each charge is electron charge, negative E. We get Ke squared over R. So that's why we just substitute K Q Q over R with Ke squared over R. Okay, that is work done too. Okay, slightly more work, slightly a little bit of work. Now, in the negative plate, already gather how many electron? How many electron? 2 electron. Already gather 2 electron. Now, I want to bring the third electron from the positive plate to the negative plate. Is it much easier compared to work 1 and also work 2? Is it much easier? The work 3, is it less than work 2? No, definitely not. Because last time, for work 2, there's only one charge at the negative plate. But now you have two electrons already, 1 and 2 already at the negative plate. You want to bring a third electron to go to the negative plate is much harder. You want to bring the third electron. This third electron, in order to come here, you need to overcome repulsive force from charge 1, repulsive force from charge 2. It encounters 2 repulsive force. So work done 3 is much harder, and that's why we say that the charge 3 interact with charge 1 and also interact with charge 2. That is U13 and U23. And that's how we get KQ1Q3 and also the KQ2Q3. You see, last time only have one potential energy to overcome. Now you have 2 potential energy to overcome because we have 2 repulsive force from 2 charges. That's why now it's like so it's like Ke squared over R times 2. Last time it's only 1 charge, repulsive force from 1 charge. Now you have 2 repulsive force. So you have a 2 electric potential energy that will be gained by this system of charge. Okay, so this work done is now 2 times the work done 3. Work done 3 is actually 2 times compared to work done 2. Okay, because we have Q1, Q2 already at the negative plate. Now you want to bring the third charge. You have U13 and U23. So it's 2 times than U12. Okay, 2 times. So work done 3 is 2 times the work done 2. Now, okay, finally, we already have 3 charge gathered at the negative plate. Now, you want to bring the 4th charge, also electron charge. You know that because all these are electron, they have the same sign, isn't it? Same sign. So negative and negative repel each other. Negative and negative repel each other. So that's why I say they have repulsive force among each other. Yeah, they have they repel each other, isn't it? Do you know that they repel each other? So this electron also being repelled by the 3 other charges. Yeah, being repelled by the 3 other charges. So now there are already have 3 electrons gathered at the negative plate. So what do you think about the Q4, the 4th charge? You want to bring it from positive plate to the negative plate. Is it the work done 4 much lower than the work done 3? Is it lower than work done 3? Is it less work done than work done 3? Of course not. Work done 3 only repelled by 2 charge. The charge 4 is repelled by 3 charge because already have 3 charge at the negative plate. So the charge 4 is repelled by 3 charge. So that's why if for work 4, you have charge 1 interact with 4, charge 2 interact with 4, charge 3 also interact with 4. We have U14, U24, U34. Q1, Q4, Q2, Q4, Q3, Q4 is repelled by this Q4 is being repelled by 3 charge. It's being repelled by 3 charge. So you have 3 work done here. You see that? 3 work done here. So compared to work done 3, now you have 3 times of work done. Ke squared over R times 3. All these charge are same electron charge. That's why I just times 3 because all these are same charge. Yeah, all these are same charge. We are only the electron flow in the circuit when charging the capacitor process. Understand? The R is almost the same. Yeah, actually they have different R, but we can say because all electrons are very close to each other, so the distance is almost the same. I can just make them all the same. So times 3. Do you see that? The first charge is 0. The second charge is 1 times the electric potential energy. the second charge is 2 times the electric potential energy. Yeah. And then the last work done is 3 times the electric potential energy. So the first charge is no work done. The second charge, you have 1 times work done. The third charge, you have 2 times the work done, and then the fourth charge, you have 3 times the work done. So you see, it's becoming harder and harder when charging process. That's why I say the graph is the area to bring the charge. That's why the area is increasing below the graph. Do you see that? Now we look back to our context here. Now let's talk about first the initial process. Relate to what you have learned just now. The initial process during the charging process. Initially the capacitor is neutral. So when you connect to the battery, the battery will start to extract. Will start to extract the electron from the positive plate to go to the negative plate. You see that electron the electron will start to extract from one plate and then together at the other plate. Initially, the capacitor is neutral. So that means I can say that it's like the first, like this one, the zero work done here. Initially, the negative plate, there's no electrons there. So for the first electron is zero work done. That's why you see the graph is at 0. So very little work since no repulsive force because it's neutral. At the negative plate, it's not negative yet. There's no charge there yet. So the first electron to go there is very easy because it encounters no repulsive force. Actually, no work done at all. 0 work done. That's why the area under the graph is 0 for the first electron to go there. Very little work. But as the second electron transfer out. Now you already have after the first electron reach the negative plate. Now you already have built up 1 negative there. You build up one negative. Okay, 1 negative. Now you want to bring a second electron from the positive plate, go to the negative plate. The second electron will start to experience the second electron. The second electron will start to experience the repulsive force from the first electron. So you have 1 times of electric potential energy. Okay, 1 times of electric potential energy. So the graph increases. So you have certain area already. You see this area. You have a certain energy stored already in the system. Okay, that is the second electron. Now the third electron, when you charge a capacitor, the third electron extracted out from the positive plate to go to the negative plate. Now the negative plate already have 2 electrons, isn't it? So the same case as this charge 3. You want to go to the negative plate, you experience 2 repulsive force. So now the electric potential energy is 2 times already. So you have 2 times work done already. You understand? It's even harder than the work done 2. That means twice the work already. Last time it's only 1 times the work. Now it's twice the work. So you see the graph. Just now is the 1 work done. Now you have 2 work done already. Do you see that? You have 2 times work done already. So that is the work done 3. Okay, even harder already. So this one, and then you want to bring the fourth charge now. You want to bring the fourth charge now from the positive plate to go to the negative plate. It experienced 3 repulsive force already. It experienced repulsive force already because got 3 charge already. So the work done for is harder, even harder. So that's why the work done is 3 times already. Last time work done is 2 times. Now work done is 3 times. So even more work done. You see, even more work done. This one. You see that? This is the fourth charge already coming. The first charge is 0 work done. The second charge is 1 times work done. the third charge is 2 times work done, and then the fourth charge is 3 times work done. You see that? Incremental. Until, yeah? So the charge increasing. We know that there are not just 4 electrons, There's millions of electrons. There are millions of electrons. So the graph increasing is impossible to it's impossible to calculate the electric potential energy for millions of electrons. How much more you need to continue the list? Yeah, continue the list. This is just only 4 electrons. How about millions of electrons? You want to calculate by this microscopic way? Definitely not. We use this macroscopic. This is we call microscopic way to find the energy, and this is the macroscopic way to find the macroscopic way to calculate the energy. So there are millions of energy to calculate up to maximum charge. Millions of electrons has already traveled and gather at the negative plate. So now the negative plate has maximum charge, achieve this max EMF, voltage equal to EMF. So that's why the last electron is the hardest. The last electron to reach the negative plate is the hardest, because a lot of work need to be done because the last electron encounter the highest, very high repulsive force from all the electrons before that reach the negative plate. You understand? When almost the maximum charge, the last electron to go there is the hardest, because it encounters all the repulsive force from all the previous electron gathered at the negative plate. That's why the graph is the highest there. You see, there's the most work done, the most work done for the last electron, That's why the graph is increasing that way. You see that? That's why it's a triangle graph. In a nutshell, the work done, the energy stored in the capacitor is a triangle shape, is half QV. So the work done also is incremental. The work done to charge a capacitor by battery is not one shot. It's not the horizontal graph. It is also a triangle. The work done by battery is also increasing bit by bit. Yeah, increasing bit by bit. Yeah, because for the initial work done is 0. Initial work done is 0. When the charge build up in the capacitor, the work done only also increases 1 time, 2 time, 3 time. So the work done also is, you cannot say work done equal to QV. This is wrong. This is wrong concept. Yeah, because this is wrong. Work done actually is also half QV. Work done is also half QV. Work done is not QV. There's one question I saw, wrong answer. Work done equal to QV. It's wrong, because the work done also incremental. What I explained just now, lengthy over here, the work done is incremental from 0 up to how many times already? The first charge has no repulsive force, very little work, until the last charge has the most work done need to be done by the battery. So it is a triangle graph. It is half QV. It is not QV. The graph is not horizontal like that. Yeah. So which is wrong. The graph is a triangle. Okay. So the work done is also incremental. So the energy stored in the capacitor also incremental. Okay. So the area under the graph is half QV. So that's all I want to say about the electric potential energy stored in the capacitor, which is the electric potential energy is equal to work done, the work done, and to calculate the work done by battery is using the same formula, half QV, or half CV squared, or half Q squared over C. So they are both equal. Okay, so that's all I want to say about this electric potential energy. Is a little bit lengthy because I involve the real concept here. Thank you for watching. Bye.